Hello to everybody out there in student land. We're looking at the topic of forces, and in particular we're concentrating on exam questions and answers over the last 3 years of the Junior Cert exam. We kick off straight away with 2008 question 7c. The question says that the globular cluster shown is a group of stars like a small galaxy. This looks absolutely nothing like a small galaxy. This looks like somebody spat on a piece of black paper. Nevertheless, gravity, we are told, is the force that holds the stars together in this formation. Give 2 effects that gravity has on your everyday life. Now, I'm a physics teacher and I struggle to come up with 2 effects, even though it should be obvious. So after thinking about it, a couple of answers that are acceptable are the following. It gives things weight, it keeps things on the surface of the earth, it causes things to fall. Okay, so it is what it is. You just learn it. It actually ties in with the next question, which is 2006, question 7a. So nothing came up on this topic on 07. Here we go. A pupil measured the weight of an apple of mass 0.2 kilograms using a spring balance and got a reading of 2 newtons. Distinguish between weight and mass. So the first line was actually irrelevant. You need to define weight and mass. So here we go. Our definition of weight. Weight is a force which is caused by a gravitational pull. And a definition of mass. Mass is a measure of the amount of matter in something. That should be in something. Both of those need a bit of an explanation, I would imagine. So if we think about it as the following, mass is a measure of the amount of stuff in something, and the more atoms that are in something, the more stuff that's going to be there, and matter is just a fancy word for stuff. Now, if there is stuff in something, it doesn't matter where you go, you will still have that something in the stuff. So if you've got a football made up of all the atoms that are in the football, you bring it to the moon, or you bring it to the planet Jupiter, it's still going to have the same amount of atoms in it, so it has got the same mass. Now, the weight of the football, however, is determined by the planet pulling down on it. So it's going to have one weight on the planet Earth. It's going to be about 6 times lighter on the moon, because the mass of the moon is 6 times less than the mass of the Earth. And it's going to be about 10 times heavier if you go to Saturn. In fact, even lifting your arm on the planet Saturn is going to be quite an achievement, because your arm will be 10 times heavier, even though there will be the same amount of stuff or matter in it. Therefore, it will have the same mass. Okay, so it's the distinction. Mass stays the same everywhere. Weight varies depending on the planet that you're on. Okay. Next question, 2006, question 9, part A. Robert Hooke made a number of discoveries, including the effect of force on elastic bodies, now known as Hooke's law. State Hooke's law. The answer is just one you'd have to learn off, and it is the following. The extension of a stretch string depends on the force applied to it. So we'll take a little bit of a look at that to see if we can try and get a better understanding of what's going on. Basically, if you look at this diagram, if there was no weight on that spring, it would have its normal natural length. As soon as you put a weight on it, that length is going to extend, and you're going to have an extension. If you double the weight, you'll double the extension. 3 times the weight, you'll get 3 times the extension. So these two are, in physics terms, we use the term proportional. So strictly speaking, Hooke's law says that the extension on a string is proportional to the force applied to it. But in this case, they will accept the extension of a stretch string depends on the force applied to it. So now we're given a paragraph of information, but basically what has happened is a student has gone and done this experiment. They have applied different weights to the spring, and as a result, they have got a series of extensions. And you can see if the extension is proportional to the force, well then if you double the force, in this case the weight, you should double the extension. So if the weight goes from 0.4 newtons to 0.8 newtons, the extension goes from 2 to 4. If the weight triples from 0.4 to 1.2, the extension triples from 2 to 6. But watch what happens over here. If we double the weight from 1.2 to 2.4, the extension should double from 6 to 12, but instead it goes from 6 to 8.6. So there's something funny happening here. And this is why we draw a graph, because a graph gives us a picture of what's happening much more, and it's much easier to tell than just looking at a bunch of pictures. So the question itself asks us to plot a graph of extension against weight, and it tells us which axis to plot them on in the grid provided. So if you were doing the exam, you would have been given a blank grid, and you have to plot those different points. So you go to 0.4 on the weight axis and 2 on the extension axis. 0.4 on the weight axis, 2 on the extension axis, and similarly for all the other points. Now you can see something interesting happening here. If when the weight doubles, the extension doubles, if that remained the case, you should get a straight line joining all the points. But yet what we see is something unusual is happening up around here. This line no longer becomes straight, or it no longer continues in a straight line. So what's happening here, it's a bit like if you've got a spring or an elastic band. If you stretch it too much, it will no longer go back to its natural length. In other words, you've broken the bloody thing. Okay, so we'll talk about that again in a second. The question it asks is use the graph to find the weight that would produce an extension of 5 centimeters. So you want to find out, okay, this is my extension axis, so here's my 5 centimeters. How will I find the weight that resulted in an extension of 5 centimeters? Well, would you believe it, you go over to the graph and down, and you find you get a weight down here of about 1 Newton. Okay, now your graph might look slightly different, so they'll probably accept an answer a little bit away from 1 Newton. In this case, they'll accept 0.9 to 1.1 Newtons. Okay, finally then, it says study your graph carefully. And why wouldn't you? It says the spring obeys Hooke's law for the earlier extensions, and then when the spring becomes damaged, it does not appear to do so. So it no longer appears to obey Hooke's law. Estimate from your graph the weight after the addition of which the law no longer seems to apply. So for what weight did Hooke's law no longer seem to apply? Well, Hooke's law basically said we should get a straight line. So at what weight did that straight line start to break off? And it seems to be down about here. So down to the weight axis to find what weight caused that, and we find it's a weight of about 1.6 newtons. Okay, so our answer is 1.6 newtons. And again, in case you had the graph drawn slightly differently than what you're given there, they give you a range. But the most powerful lesson from all of this is the power of the graph. It gives you information that's not obvious from a series of numbers. Okay, but that in itself represents all the questions that have come up on the last 3 years on this topic. Okay, Shinna will for now. We'll come back to it next year. Be sure to join us. And that's a